Hey guys, welcome to our continuation of section 5.2. We're going to start introducing variables into our rational exponent expressions and radical expressions. One thing we have to consider with variables is that they can be positive, negative, or zero. Now, when we apply the properties of rational exponents and radicals, we have to understand that because that means that sometimes we might have to use absolute value to ensure that our answer we get would mean the positive, let's say, square root or fourth root. Now, we understand that only when we are taking an even root will we have to account that there could have been positive or negative. So that's when we would need absolute value. So the rule is this: if we take the nth root of x to the n, that is just the absolute value of x. The reason being is if we look over in the example, obviously if we are taking the root of a positive number, the fourth root of 3 to the fourth, 3 to the fourth is 81. And that does give us positive 3. If we're taking the root of a negative number that's being taken to an even power, negative 3 to the fourth also gives us positive 81. So that gives us 3. So moral of the story, when we're taking an even root of a number being taken to an even power, it will always be positive. So that's why we have to put the absolute value around that variable. One thing I want to note right here is that the absolute value is not needed when it says that the variables are assumed to be positive. And we'll see that in some of our directions. But first, let's look at example 6. Simplify each expression. So instead of just cube root of 64, I have the cube root of 64 times y to the 6. Remember that we can put radicals together while we can also take them apart. So we could write this as the cube root of 64 times the cube root of y to the 6. The cube root of 64 we know is 4. Some of us right off the bat know that the cube root of y to the 6 is actually y squared. One way we know that is because we could write this as a rational exponent, that'd be y to the 6 over 3. And 6 divided by 3 is 2. Another way we know that is that I could rewrite y to the 6 as y cubed times y cubed. So I technically have two y's that I could take out front, and that would be y times y, which is y squared. What I usually do when I'm taking variables with exponents and finding a root of them, I try to make them into exponents that are divisible by the index. And if they are, that's a perfect, for instance, this was cube root. It could be fourth root, fifth root, etc. So if we look at b, I have the fourth root of x to the fourth over y to the eighth. The first thing I'm going to do is separate this radical into two different and take the numerator and denominator separately. Now, as I mentioned before, if the power of your variable is divisible by the index of your root, that is a perfect root. And both of these are that, because x to the fourth root of, that would just be x to the first. And this is a case where we will need absolute values because that's an even root. So that x could have been negative, right? And then the fourth root of y to the eighth, 8 is divisible by 4. It goes in there 2 times. That would be y squared. Now, we don't need absolute value bars around the y squared because when we square something, it's going to be positive anyway. Okay, example 7. Write each expression in simplest form. Assume all variables are positive. So this takes out me having to remember to put absolute value bars on my variables, which is nice. All right, letter A, the fifth root of 4, a to the 8th, b to the 14th, c to the 5th. Okay, so I'm going to first separate or maybe have to rewrite some of my variables because I see that they aren't perfect degrees of 5. For instance, 8 is not divisible by 5, 14 is not divisible by 5, 5 is, so that's great. But the other two I'm going to rewrite. I'm going to rewrite a to the 8th as a to the 5th times a cubed. I'm going to rewrite b to the 14th as b to the 10th times b to the 4th. And then leave c to the 5th as is. Now, I have a to the 5th, which is a perfect power of 5, b to the 10th, which is a perfect power of 5, and c to the 5th, which is also a perfect power of 5. Or 5th power, excuse me, not power of 5, I apologize. So what that means is I can take the 5th root of those and bring them out front. So the 5th root of a to the 5th is a. The 5th root of b to the 10th is b squared. 10 divided by 5 is 2. The 5th root of c to the 5th is c. And then what remains under the radical will stay there. And that is my answer. Looking at B, I see that I have a radical in the denominator of a fraction, which is definitely a big no-no. But before I try to rationalize the denominator, I'm going to simplify that radical. I have the cube root of y to the 8th. Well, let's see. What is the greatest multiple of 3 that is less than 8? That would be 6, right? Y to the 6 times y squared would be equivalent to y to the 8th. So this y to the 6th is a perfect third power, and that would be the cube root of y to the 6th would be y squared. So I'm going to start writing over here. I have a little bit of work to show. So I have y squared now times the cube root of y squared. So the only thing that is not okay here in the denominator is this part. So what I want to do is I want to rationalize this denominator. So what I have to multiply by is the same thing on top and bottom, and it's what's going to make this the cubed root of y cubed, because that's just going to be y, right? So that means I'm going to have to multiply this by the cubed root of y to the first. And I'll show you in 1 second. So I do that on the top as well. Because what happens there, let me get rid of this so you can see. Because these are both under cube root, that results in the cube root of y squared times y to the first is y cubed. Okay, so that works out nicely. So in my numerator, I have x times the cube root of y. And in my denominator, I still have this y squared from the front times the cube root of y cubed, which is just y. And then one more step, that would be x times the cube root of y over y squared times y, which is y cubed. And I've rationalized my denominator. Now I know that one's a little complicated, and we'll go over that one again in class. Okay, letter C. Now I have some rational exponents and some coefficients. First, let's look at the numbers. 14 over 2, I can reduce that to 7. So I'm going to write 7 in the numerator. Then I have x to the first over x to the 3/4. Okay, so that's x to the first. Remember, when we are subtracting fractions, we need a common denominator. Well, that would be 4/4, right? That would be 1, and then I have to subtract 3/4. If I take 4/4 minus 3/4, I get 1/4. That's a positive 1/4, so that x to the 1/4 is going to be in the top. Okay, the last thing, let's see here. I have y to the 1/3. I don't have any other y's, so I'll put that on the top. And then z to the -6, that can't be in the bottom, so I bring it up top. Oh, I guess everything's in the top, and that would be my final answer. Letter D is actually pretty simple. We see we have 5 times the square root of y, and we have 6 times the square root of y. So 5 rad y plus 6 rad y. You just add 5 and 6, and you get 11 rad y. And finally, I have 12 times the cube root of 2z to the 5th minus z times the cube root of 54z squared. Unfortunately, these don't have the same thing under the radicals like D did, so we have to figure out if we can simplify these radicals to be able to combine them. So I have 12 out front here, and I have the cube root, so I could rewrite this as 2 times z cubed times z squared, because that means I can take a z out. Okay, so that would be 12 times the cube root of 2z squared. All right, then I have minus z times the cube root of 54. Now, 54 is obviously not a perfect cube, but if we start factoring it down, it is divisible by 2, and that's 2 times 27. Isn't 27 a perfect cube? That's 3 cubed, right? So I could write 27 times 2 times z squared. I can't break that down at all. So this 27 is a perfect cube. And the cube root of 27 is 3. So I'm going to bring that out with my z. That's going to be minus 3z times the cube root of, left under my radical is 2z squared. Now, do you notice what I have left over under my radical is the same in both of these? So, oops, I lost my z over here somehow. Sorry about that. That was from the z cubed. Brought that out front. Excuse me. So now I have 12z times the cube root of 2z squared minus 3z times the cube root cube root of 2z squared. So those are, again, like terms like we had in D. So I just need to take this 12z and subtract that 3z, which gives me 9z, and that'd be times the cube root of 2z squared. And that is our answer there. We're going to put it all together again in class tomorrow.